Hi everybody. Today I'm going to talk to you guys about the change in momentum. If you recall all the way back to video 38, I showed you a formula and I told you that the left side was the impulse. And then I kind of left the right side alone. I didn't really talk about it much. You may have noticed that it looked very similar to what we talked about in video 39, which was about momentum. And so we're going to talk about how the two videos, 38 and 39, fit together. And it has to be, we have to go back to that original formula, that 7.1 formula, to be able to do that. Okay, you might notice that I copied this stuff here from that video 38 because we have to start in the same place that that started. And so I'm going to go ahead and do that here. I'm going to start right there, of course, with our Newton's second law. And so Newton's second law says the net force acting on a mass produces an acceleration. And to be able to calculate it, we take the net force and we divide basically the mass to figure out what the acceleration is. It's often written this way though, just as a way to remember it, because it's a little bit easier to remember, F equals ma. It's not the way Newton wrote it, but that's the way it's easier to understand, I think, or to memorize. That's our formula 4.2. And we combined that here with the acceleration definition, which was the change in the velocity vector divided by the change in the time, which was our formula 2.3. You may notice that we've got an acceleration here and an acceleration here, and so we can fit this into this space right there. And we end up with this formula down here. That formula is just a transitional formula, so it's not going to be on your formula sheet, because the next thing we're going to do is to modify it slightly. So we're going to multiply both sides by delta t, and then we end up with this. This F times delta t equals m times delta v. Now, it may not seem like it's in simplest form, but in reality, there's something useful to be said about the stuff that's on the left, and also something else useful to be said about the stuff that's on the right. And so leaving it in this form is totally fine. In fact, it's our formula 7.1. You may recall that this stuff right here was the focus of our 38th video, and we called it impulse, and we gave it the capital letter J as the variable to talk about impulse. So impulse is this F delta t. It's the amount of net force that's applied over a certain period of time. And we are multiplying those together, we get this product, and that product will tell us some interesting things about what happens, what is actually happening to an object. This other stuff, though, we didn't talk about, and so you may have seen the parallel between this m delta v, and the thing that we talked about in the 39th video, which was this formula right here. The momentum, which was a vector, right, is equal to the mass times the velocity. Whoops. Like so. And so this formula, which we got in the last video, has a lot in common with this m delta v, right? mv, m delta v, they seem very similar. And in fact, what we can say is this, that m delta v is a way of describing how the momentum is going to change when an object changes its motion. So we take this stuff right here, this right-hand stuff, and we assign it the variable delta p. Delta p stands for the change in momentum. And so this right side is the change in momentum. So this formula is known to physicists as the impulse momentum theorem, or you could say impulse equals change in momentum. So if I were going to write that out, I'm going to write it out up here. Let's say I'm going to say J, which is the impulse, is equal to the change in momentum, like so. That's a kind of a shorthand way of writing it, which is kind of nice. But it's important for you to remember that the change in momentum is the mass times the change in velocity. Typically in collisions, particularly in the laboratory, the mass doesn't change for the object that you're analyzing. It's only the velocity that changes. And so we're not so worried about that being a constant because, again, typically when we're talking about stuff in the lab, it's not going to change. Now, real quickly, this is a drawing made by our textbook author, and our textbook author used to be a boxer. And so a lot of the descriptions that he gives tend to be boxing analogies. for this reason, because that's the world that he comes from. And so here he has a boxer who's moving their head back when they get punched, right? So the fist is coming in with some velocity. Obviously the fist has some mass. And as the boxer gets punched, he moves his head backwards. Whereas on the right side, we have the same boxer, for whatever reason, maybe he's taken too many blows to the head at this point, decides he's going to push his face into the fist as it comes towards him. And so the question is, which one is better for you? Now, you probably know, or at least could try to figure it out. Hopefully not from experience. But I know he knew, the textbook author, from experience. And so here's what happens. This fist, so I'm going to just sketch it for a second here. So, oops. Gosh darn it. There we go. Is coming in with some velocity, right? And that fist has some mass. And so since it has mass and velocity, we have to say it has momentum. And so it's coming in with some momentum, but when it hits the face, it's going to stop. And so wouldn't you agree that if it had originally had some momentum and then it went down to 0, that there was a change in the momentum? And so if there's a change in momentum, then there must be some sort of impulse that's being applied to do that, right? If there is a change in momentum, it must be the result of an impulse right there. And so impulse could be the force times the time here. So as you move your head back, okay, you have to change the momentum a certain amount, but you can do it in a longer period of time. And so as this delta t gets bigger, we know that the F gets smaller because we still have to change the same momentum here. The fist still has to go from its velocity to a stopped position. And so as a result, by changing the amount of time, by backing up your face, you decrease the amount of force. And so it doesn't hurt as bad. Whereas if you're not so bright and you're like this guy, if you put your face into it, now all of a sudden you're making the delta t very, 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 very small. But the momentum of the fist still has to change by the same amount. And so as a result, it still has to have the same impulse, which means if delta t gets small, F gets very large. And so this guy is going to get knocked out much faster than this guy is over here. Now, this could apply for any particular situation. So here I've drawn a car, and the car has a mass of 1,000.0 kilograms, and currently has a v sub 1, an initial velocity of 0. Sorry, there we go. And so it's not moving at all. And so if I wanted to figure out what the momentum was, it would be pretty easy to figure it out, right? 1,000 times 0 gives me a momentum of, at least an initial momentum, of 0 kilograms times meters per second. Okay? Now let's say you hit the gas, and so you want to get your car moving. And so by hitting the gas, what you're really doing is applying an impulse, right? The engine applies a force for a certain period of time, and we call that an impulse. So what's the result of any impulse? We know from here that the result of any impulse is a change in momentum. So let's look. Your mass now is the same, right? Probably in the real world you've decreased the mass slightly because you've used up some gasoline. But that's more of a calculus problem, and I'm betting you don't want to do that. So let's just assume it's constant for now. It's probably pretty close. So the mass is still 1,000 kilograms, but now the velocity is, at this second time, 10.000 meters per second. And so what's our new momentum? Well, it's easy enough, right? 1,000 times 10 gives us a new momentum of 10,000 kilogram meters per second. So, did the momentum change? Sure, of course it did. If there was an impulse, the momentum must change, right? And so it went from 0 kilogram meters per second to 10,000 kilogram meters per second. And so the change in momentum can be thought of also as just any old definition of change, right? Any change variable is going to be the final state minus the initial state, just like delta v right here, or delta t. Those are the final velocity minus the initial velocity. This is the final time minus the initial time. So delta P is the final momentum minus the initial momentum. So 10,000 kilogram meters per second minus 0 kilogram meters per second gives us a change in momentum of 10,000 kilogram meters per second. And because it's increasing the speed, we know that the velocity is changing in the positive direction. So we have a positive right there, just to indicate that it's a vector, right? So in this case, we're going to be doing one-dimensional vector problems, which means we're going to have to define one side as positive and one side as negative. And so in this case, I defined the right-hand side as positive, which is typical. And so there was a positive impulse, meaning there must be a positive change in momentum. Okay, I think that's it. If you have any questions, please let me know. Thanks.